Electric vehicles have caught the fancy of automakers and policymakers alike in India and around the world. With the government's push to make India a 100% EV nation by the year 2030, automotive companies are carefully treading into the EV space to expand their portfolio. Now we have a presentation on Virtualization of EV Drivetrain V&V by Shitalkumar Joshi, Head Electrification India Asian ANSYS. Over to you, Mr. Joshi.
Good afternoon, all. Thank you, ET, for organizing this wonderful event in virtual mode. COVID has impacted automotive industry worldwide, but the least affected segment was EV, and it's expected to grow rapidly in coming months. To meet this rapidly growing automotive demand worldwide, there has been a strong emphasis on front-loading the verification validation methods during the product development. That's the topic of my talk today. My name is Shitalkumar Joshi. I head Electrical and Electronics at ANSYS for India, ASEAN, and Australia, New Zealand. So here is the agenda of my talk. I'll introduce the topic briefly, and then we'll discuss about component and system verification, and I'll end with a use case on battery verification. Okay, so before getting into detail, just briefly introducing my organization. We come to ANSYS. ANSYS is a simulation global leader. We have about 4,200 employees. We have about 45 to 50,000 trusted customers. 97 of Fortune 100 companies use ANSYS. And we are focused only on simulations. We are CAD, PLM, IoT, agnostic. We are open architecture, making our customers successful in the areas or megatrends like digitization, 5G, ADAS, autonomy, electrification, addition, and digital twins. So with that intro, let me move to next slide. And this is about, this slide specifically says about what we are aiming from the virtualization proposal that I'll be discussing in subsequent slide. This slide is about what we are expecting from virtualization proposal that I'll be discussing subsequently. Now, virtual simulation has been part of automotive product development for quite long, but there has been a need to have a digital continuity across the product development cycle. There is a need to remove silos between software world and physical world. There's a need for enhanced model on interoperability between the verification validation process, software, and 3D design groups. Because of these gaps in current design process, lots of cost items are committed at very upfront, very early stage. And as the cost gets committed, freedom for the change on the design, freedom for change in component selection gets reduced and gets restricted. Here, validation exercise comes towards the end. And as mentioned, that validation is very expensive. So to deal with this problem, companies are now moving to what we call is virtual prototyping or rapid prototyping. I must have a disclaimer that rapid prototyping, we are not talking about 3D printing because that's the term used over there as well. What here we are discussing about is we essentially bring our last validated design, if there is a virtual validation platform exists. We take the last validated design, then bring the new requirements, and then change few modules, few components in a virtual mode, and check if this change meets the new design and performance validation is possible or not. So this can be done at very early stage, okay? And if you can see over here, by doing this step, the design flexibility increases and cost commitment at early stage decreases. This blue new triangle, that is rapid prototyping. That's precisely is the change that's from constrained design process to more flexible design process, and that's getting knowledge from old system to new system. Now let me share what happens to specific to EV. And EV typically kind of requirement starts with branding and then what sort of vehicle segments is. Post that, it's mostly kind of IC vehicle is converted into EV. So companies majority companies in the world and India also kind of starts as an integrator. Many design components like motor, battery are outsourced and those components are integrated. This process has advantage because it helps outsourcing the design and accelerating time to market, but it also has its own challenge like achieving the system efficiency and range and all those issues. Moving forward, OEMs are moving for more in-house designs. So in-house designs, all components are designed and developed. And for that, an extensive virtual simulations through FEA, CFD, electromagnetic is done. And these methods are quite well evolved, quite well developed. Best practices are there in place. Due to very large number of design combinations to be studied because of a complex interplay between hardware and software, MBAC methods is taking over as a key design process development. Here is MBAC is described in block diagram. All critical components like EV drivetrain, battery, motor, electronics, inverter, clutch, wheel, mechanical, vehicle dynamics are integrated. Software component is integrated. Okay. In fact, one of the most important thing to remember is we are not leaving behind the 3D studies that we just described few minutes back. In fact, all 3D studies can also be integrated into MBAC framework, and those can be integrated through lightweight behavioral model that can be derived from these 3D studies. Okay. So let me also describe very briefly about the critical modules of motor batteries. So I'm not going to get into detail of these slides, but just to mention over here that when you are when you do not have a physical component ready, when you are design mode, these are all the simulation practices that are quite proven that are being practiced globally, and all of them have a very strong matrices like time to market or cost saving, and then all in place. Okay. In fact, what we are seeing is if we combine machine learning further, the return from this component level or design processes increases considerably. Now, next I'm going to show about this component level design processes, how we can use into verification, validation, and testing methods. So this is a kind of standard testing scenarios or steps that all typical kind of EV model have to go through. It starts with component level model in loop, software in loop methods, component level hill, and then rig design. Here, typically, if you dissect this further and see at the component level, motor, battery, subsystem designs are first verified. Here, software and physical components both are studied. Hardware components is studied through some low fidelity model. But what the trend that we are seeing globally is using high fidelity model through 3D simulations, or maybe if test data available, but most likely not, because this is a like early stage verification validation we are talking about. And that's how it's helpful. Before any prototype, you could do model in loop and software in loop. Similarly, on hardware in loop, also the same simulation model based behavioral models can be used. Now, what is the advantage of doing this? That you don't have to wait for a motor to be built and putting on bench test and getting efficiency map generation, then do a validity. Much before that, you would be accessing the performance of the motor and battery. On the same way, you could access the performance of entire powertrain subsystem, right, where you include power electronics, motor, battery all together. And going forward, finally, the vehicle subsystems, a vehicle system level test, where you're also having the vehicle dynamics and road condition and all. So essentially, what you see over here in the entire map, mill sill for component level and powertrain is already virtualized. HIL methods are in process of virtualize, where more virtual plant models are getting used, right? And also I'm going to talk next about the entire virtual system model, where how you can create the scenarios, put the terrain, use the software plus other models that you develop throughout your product development cycle, and you can integrate to do a virtual system study test. This one shows a model structure for virtual performance validation. We are not getting into detail. Just want to highlight over here that in this model structure, you can have a driving scenario sitting at the top, and that interacts with the vehicle controls, vehicle dynamics, and BMS motor controller, and that is integrated with the physical models for battery, motor, inverter, transmission, and all. This physical model comes from either 3D simulations, that is the most likely scenario if you do not have any prototype ready, or it can be some test data also can be used, or even 1D low fidelity models also can be used if the 3D models are not ready. So that's the way the models stack are generated, platform is generated. Once this platform is generated, okay, it would take time because calibrations, model best practices, component model fidelity, all those things are very important for a robust and accurate virtual validation platform. Once the virtual platform is ready, that has a huge advantage. It provides, ability to perform a large number of drive validations, like through vehicle parameters, wheelbase, and size, and so on, requirements, acceleration demand, road conditions, the new vehicle requirements, or change in requirement through midway of product development, or even meeting the constraints that are required by safety. Everything can be kind of studied in a virtual mode. And not only that, you could add scenarios for beyond EV, like if you can integrate autonomous scenarios as well, like sensors, lane change, traffic, HVAC demand, and so on. So this provides a huge flexibility, and finally this results in a robust virtual platform that can be extensively used for one, validation, second, calibration, and third, even extending to prognostication of the vehicle and vehicle components. So how it is done, I'll just share a short video, but before that, this can be done by combining all vehicle models, be it motor, battery, BMS, inverter, ECUs, vehicle dynamics, combining that with the vehicle environment, and that combining with it with the software development. You can kind of then use AR, VR technologies to create a scenarios. The scenarios, you could over here use OpenStreetMap. Over here, we have used VRX and Twin Builder Simulator in this example. Essentially, you can use this platform for battery drainage, acceleration, checking battery performance, range, SOC temperature, or any other virtual sensors that otherwise kind of you would want to do it in a physical world. So with that description, let me move to the short video, which is kind of demonstrating this entire capability or the entire workflow that we discussed so far. So let me start this video. So here we start with creating a virtual scenario, and here we have taken a kind of in this demonstrator we have a small patch near in Pune on a Bombay-Bangalore highway, and this patch can be imported to create the scenario. The scenario we are creating over here is having a certain set of elevations. We can add road details and so on. Post that, now we are now all integrating the EV powertrain model. So first what we did is kind of created a scenario. Now we are integrating the EV powertrain model. So here we have a battery. Battery, if you click to, you will see the 4 modules, and each module, if you go in more detail, each module would have kind of over here like 80 cells or so. And each cell here has a physics-based model. So either it's coming from fluent or kind of electromagnetic in motor and so on. Each components are having a physics-based model. Over here, everything is integrated along with the vehicle dynamics as well as the road scenario. So what it would look like finally is what you see over here. You can kind of define the scenarios. You can have the vehicle kind of see the vehicle moving over here. As you move, you can see the temperatures of the all cells over here. Temperatures, SOC, all battery health parameter you can measure for all cells. And then here kind of I'm also dynamically plotting the temperature for a certain number of cells, and it sees that as the elevation increases, the power requirement increases so the battery temperature also increases, and then probably as the demand for power reduces, automatically temperature starts dropping for the battery over here, as you will see in this virtual scenario simulations. So what we have done over here is we have combined physics. We have combined physics from each component. We have combined the software from each component. We have combined vehicle dynamics. We have combined the scenarios, maps, and finally creating a virtual use cases, which will be used for verification validation of the EV performance. So with that, I'll end my talk. Thanks for your time and attention, and I hope it provided a good insight of where industry is moving towards adopting the virtualization of verification practices. Thank you.
Thank you, Mr. Joshi, for sharing your knowledge on EVs. Ladies and gentlemen, keep asking questions by typing in the chat box. The purpose of this event is to discuss and deliberate all the possible questions and challenges around the EV space. Let's proceed to the next session.